My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 419. In this lecture, we will try to understand residuals, loss function and gradients. We have seen in the previous lecture, that is at the end of boosting, we build a model with k plus 1 base learners, which is nothing but fk of x equal to sigma I equal to 0 to k alpha I hi of x. Now the big question here is, how do you find alpha i's? How do you find alpha i's and how to compute hi of x? To compute hi, we need to get residuals. So let's understand residuals, loss function and how they are related to gradients. All these three concepts, that is residuals, loss function and gradients, are extremely important to understand the concept of gradient boosting. Gradient boosting is very popular form of boosting, extremely useful in the real world, extremely popular by the way. So what is the residual? Let's understand the concept of residual. Residual is nothing but, as we saw in the previous lecture, residual at the end of stage k, we can write the residual at the end of stage k as yi minus fk of x. That is error of I equal to yi minus fk of x. If you have to train a model mk plus 1 to this, we would give what will you give? Xi comma error of I, isn't it? How can I train this model mk plus 1 using xi comma error of I, isn't it? What is this? This is what we discussed in our previous lecture. This error I is called residual. This is called, what is this? This error I is called residual at the end of stage k. Now, at the end of the day, whenever you solve a machine learning problem, all the thing that try to do is, we try to do some form of loss minimization. For example, in logistic regression, minimize logistic loss for a classification algorithm. If you remember linear regression, in the case of linear regression, we minimized squared loss. Similarly, in the case of support vector missions, we minimized hinge loss. We learned all these concepts when we learned support vector mission, linear regression, isn't it? And support vector mission, linear regression, even logistic regression, isn't it? Let's revisit the concept of loss minimization. So given a residual like this, what is a residual? We discussed. Given a residual at the end of stage k, I can define loss around it. So let's define a loss function written as L. What is my L? L is basically, what is this L? L is loss function. This loss function is dependent on the true class label. What is my true class label? Yi is my true class label. And the model at the end of stage k. What is my model at the end of stage k? That is fk of xi, isn't it? Let's, like regression, let me take regression because it is easy to understand. Now let me consider this one. What is this loss? Squared loss. Let's take regression because it is easy to understand. Of course, we can understand it using, you can make use logistic loss, even you can make use hinge loss, isn't it? I can say logistic loss, or you can even, let me repeat, otherwise let's take regression because it is easy to understand. Of course, we can understand it using logistic loss or hinge loss also. It's just easy to understand the concept because mathematics is much more similar when we use squared laws, isn't it? When we use squared laws and linear regression. We are trying to solve a regression problem, not a classification problem. Let's assume my loss is basically my squared loss. And what is the formula for squared loss? It is nothing but, what is squared loss? It is nothing but yi minus fk of x. This is error. What is this? Is square. Therefore, this is known as squared loss. It's called squared loss, and this is what we minimize. Sum of this across all points. This is squared loss. This is what we minimize. Sum of all these, isn't it? This is my loss, isn't it? What you have to do? Just let me calculate. I have L. I am assuming this fk x of I as zi. Therefore, this will become L of yi comma z, yi minus, instead of fk of x I am writing zi. Just let me differentiate this loss function with respect to zi. We know what is the formula for differentiation? D by dx of x power n equal to n into x to the power of n minus 1. This is 2 into yi minus zi whole to the power of 2 minus 1. Again, you have to differentiate. This is 0 with respect to a partial differentiation. With respect to zi means yi constant 0, zi with respect to zi 1, 0 minus 1. Therefore, you will get minus 1 into 2. This is dou L by, what is this? Dou L by dou zi. You are getting minus 2 into yi minus zi. That is basically, I can take this minus here, minus dou L by, what is my zi? Zi is fk of xi equal to 2 into yi minus, what is zi? Zi is basically fk of xi, isn't it? This is, what is this? What is this? This is yi minus fk xi is my residual. It's my error, isn't it? What is this? Just see, this is not, this is, what is this? Minus dou L by dou fk of xi. This is the negative derivative of the loss function, isn't it? L means loss. This is negative derivative. Minus means negative. Dou means derivative. Whose derivative? Loss function's derivative with respect to model. What is my model? fk xi. I have at this model, you have at stage k. This is a negative derivative. Derivative can also be thought of as gradient, isn't it? That's what we discussed in previous lectures also. This can be thought of as a gradient. You can think of the, you can think of the negative gradient. Negative gradient or negative derivative. Basically, gradient means grad. So let's assume instead of using the word derivative, I am using gradient here. So negative derivative of your loss function with respect to the function at the end of stage k, that is fk xi, isn't it? This is function fk xi can be thought of as residual. This is it not residual? Can be thought of as residual except for the factor 2. Just neglect 2. Isn't it? Now let's assume I ignore this 2. Let's assume I ignore this 2 for now. Let's assume I ignore this 2 for now. Or you can think of negative gradient. This is negative gradient, is it not? This negative gradient is proportional to residual, isn't it? Is it not? Yes, this is negative gradient. This is negative gradient. Gradient is proportional to residual. Residual is as I am just if you skip that number 2. So what we can do here, this is the big leap in gradient boosting. The reason gradient boosting is so powerful, the reason first let me repeat, this point is very important. Negative gradient is proportional to residual. Yes, the reason, this is important. The reason the gradient boosting is so powerful because of this analogy. What is the negative gradient can be thought of as residual. It is approximately equal to residual, often called as pseudo residual, isn't it? This is also known as pseudo residual. Yes, at any stage I try to build this model hi of x. What is my hi of x? Using xi and error I, isn't it? What is this? Error I is yi minus fi minus of x. Yes, yes. Now, instead of taking my error at any point I as the residual, this is yi minus fi minus 1 of x is the residual at point I. Instead of this residual, I replace error at any point I with pseudo residual. Yes, I am replacing this residual with pseudo residual. Why? Because we have result, isn't it? What is that? What is that result? Negative gradient is proportional to residual. Therefore, I can now instead of residual, what if I replace error at any point I with the pseudo residual? And what is the pseudo residual? The pseudo residual is the derivative of loss function. This is my pseudo residual, derivative of loss function with respect to fi minus 1 of x, that is minus dou L by dou fi minus 1 of x. When we use simple squared laws, your residual is very similar to your residual. That's what I am saying. Your residual is very similar to negative derivative or negative gradient. Derivative means gradient. So what if I make the leap, instead of training on the residual every time, what if I train on pseudo residual? It has huge advantage because I can have any loss function. You might ask, why are you training on pseudo residual? Why can't we train on residuals? The big advantage of pseudo residuals provides us pseudo residuals work with any loss function. This pseudo residual work with any loss function. That is important. This work with any loss function, isn't it? Pseudo residuals can work with any loss function of your choice as long as we compute derivative. If it must be differentiable. If you are able to compute derivative, we can make use minus dou L by dou fi minus any loss function which is differentiable. What is this? It is applicable for any loss function which is differentiable. This is big idea in gradient boosting. For example, let me argue this way. If I want to build a random forest, let's say minimize hinge loss, isn't it? Can I do that? Not possible. Can I do that? Isn't it? What it says? If I want to build a random forest, let's say minimize hinge loss. But hinge loss is related to support vector missions, isn't it? It's not random first. Can I do that? Not possible, right? Because each of your decision tree is minimizing some entropy. Decision trees are related to entropy, isn't it? Decision tree. Let me repeat question. If I want to build random forest, let's say minimize. Intention is minimize hinge loss. Can I do this? Not possible. What is the reason? Isn't it? Each of your decision tree, random forest means decision tree. Each of decision tree is minimizing with some minimizing entropy, not hinge loss. Isn't it? Minimizing entropy. It's not minimizing hinge loss, but with gradient boosting, but with the gradient boosting, like ideas, I can minimize any loss. Not only this one. With the help of gradient boosting, I can minimize. With the help of gradient boosting, one can minimize any loss. any loss, as long as this is differentiable. Condition is only differentiability. Differentiable, isn't it? That's a big advantage that's the pseudo residual gives us. By approximating residuals with the pseudo residuals, we can optimize our problem for any loss function we want, which was not possible otherwise. This is the reason why gradient boosting is so popular. Actually, in lot of cases, if gradient boosting can be used, it tends to perform slightly better than random forest, because my business might say that I want to minimize hinge loss. What is the which is the impossible with random forest, isn't it? I want to minimize hinge loss, which is impossible with random forest, which is not easy with random forest. In general, gradient boosting big advantage is it can work with any loss function. It can work. Gradient boosting big advantage is it can work with any loss function, any differentiable loss function. If you speak strictly, it works with any differentiable loss function. This is the big idea. This makes it super. This make it super useful. That's important, isn't it? Gradient boosting is not only type of boosting. There is something called, yes, let me repeat. Gradient boosting is not, yes, anyway, this I already discussed, isn't it? Just see, that's what it happened. Dou L by dou x minus dou L by dou f k x. This is I'm approximating. That's what we discussed. This is the biggest advantage. Your pseudo residual, I can say your pseudo residual is directly, if you remove this, just directly proportional to residual. Yes, anyway, this I already discussed. Let me continue my discussion. Gradient boosting is not the only type of boosting. There is something called adaptive boosting, isn't it? There is something like adaptive boosting or ADA boost. Even in ADA boost, you can't put any loss function. ADA boosting try to minimize the specific type of loss function. Gradient boosting is basically says if you have bias mode, if you have base models which have high bias, I will combine them using pseudo residuals. And the way I do pseudo residuals, this is the most powerful idea. Pseudo residuals is by using negative of the derivative of loss function with respect to the function I have at stage I minus 1. That is minus dou L by, what is that? Basically minus dou L by dou f of I minus 1 of x. This I already discussed. This is the big idea of gradient boosting, which makes it super powerful. We will look at exact gradient boosting in my next lecture. Time being, just go through this lecture, and if you are not able to follow, just refer it once and twice. If you have any difficulty, please keep comment. In my next lecture also I will continue my discussion on gradient boosting. Thank you very much.